So turn to page 132. This is chapter 3.2. And now we're going to talk about why we learned about parallel lines, transversals, why we talked about corresponding angles, alternate interior and alternate exterior angles, and then consecutive interior angles. So to begin with, every one of these postulates or theorems that we're going to talk today about, they begin like this: if two lines are parallel. Okay? If these two lines are parallel, then we can know some things about them. Okay? If they're not parallel, then no. None of this corresponding angle stuff, none of the alternate interior angle stuff, none of that matters. All right? So we're going to begin if these two lines are parallel. And for that, we really have to talk about, are any two lines parallel? That you can have an argument about that. So on the quantum level, that means very, 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 very small quanta, like the very smallest particles. When you start looking at really what matter is made up of, this type of geometry, Euclidean geometry, doesn't work. There are no points, there's no lines, there's no planes, and so there's no parallel lines. It just doesn't happen. All right? When you look at vast areas of space, okay, when you talk about, well, space is curved, gravity is curved by things, light is even curved, it doesn't go straight. Okay, so there are no parallel lines. If you try to use Euclidean geometry to get a spaceship from Earth to Mars, it's not going to work. Okay, now however, if you're building a house, if you're making a desk, if you're trying to drive a car somewhere or even an airplane, okay, Euclidean geometry will work. So for most of the stuff we do, normal size objects on Earth, this stuff works. But it all starts with this. We have to understand that these two lines are parallel, meaning they're in the same plane, right? They're in the same plane, and they're equidistant at all points. So if I choose a point here, if I measure over, if I measure at a right angle, that distance right there, this distance right here, they're congruent, aren't they? Okay, that's the deal with parallel lines. They have to be in the same plane and they have to be equidistant. They don't ever intersect. They never get closer, they never get further. So with these parallel lines, the first thing we're going to talk about is the consecutive interior angles postulate. Now, if you look in the book, it's not called a postulate. They call it a theorem. But it's not a theorem. They just call it a theorem in this book. It's actually a postulate. There's no proof for it. There's no real way to say this is absolutely the way it is. But, hey, notice my arrows aren't on the ends? What does that mean? Okay, these lines are parallel. If I draw a transversal, and it doesn't matter where I draw the transversal or how I draw it. So this is line L, this is line M. We'll call this line T for transversal right there. If I draw the transversal and I look at corresponding angles, let's look at these two. What do you guys think about them? They're congruent. I mean, do we need to measure them to tell? Or can you just tell? What do you think? I mean, if you were making a building and these two angles being congruent meant the building stood up or didn't stand up, would you bet on it? Yeah, I do it all the time. Okay, it's just we look at it, it has to be that way. Yeah.
So this is on topic, but a little bit off topic. If we make theorems based off of postulates and we don't really have a way to prove postulates,
Exactly. Well, let's start back even further than that. We talk about points, lines, and planes. which are undefined terms, meaning there's no actual definition for what a point is. We just all have an agreement about what we kind of consider it, how it is. If that's not true, okay, if points don't really work that way, if there are no points, like in the quantum world, there's not a point. And if you look at it, it's not where you think it is, or it may only be there because you looked at it. This is a whole big thing, okay? If none of that is actually true, then none of this is true, okay? But the thing is, I use Euclidean geometry all the time, okay? It works. I'm telling you, I bet my life on Euclidean geometry all the time. I used it to build a house that has cement walls, not just the basement cement walls, upper story cement walls. Euclidean geometry tells me when things are perpendicular, when they're parallel. Okay? It tells me it's going to stand up. And does it stand up? Yeah, it absolutely does. Okay, it works. So our experience here on Earth is it works. Okay, this actually gets you to the right place. It makes things come out the way they're supposed to come out. So yeah. So we look at this, and this is the corresponding angles the corresponding angles postulate. I'm just going to abbreviate it. Postulate. Okay? And it begins like this. If two lines are parallel. Every one of these today begins that way. If two lines are parallel and they're cut by a transversal, what do we know about the corresponding angles? They're congruent. Not that they're equal, not that their measures are equal, that the angles are congruent. So we know angle 2 and angle 6 are congruent. We know angle 3 and angle 7 are congruent. And we know angle 4 and angle 8 are congruent. P.S. What about 1 and 3? What's that relationship called? Vertical angles? What do we know about all vertical angles? Okay, they're congruent. So if 1 and 3 are congruent, and 1 and 5 are congruent, then 3 and 5 are congruent. Now that's a theorem. Okay, that is a theorem. So if I can begin with the corresponding angles postulate, saying angle 1 and angle 5 are congruent, and then I say angle 1 and angle 3 are congruent because they're vertical angles, because of the vertical angle theorem, then I can say angle 3 and angle 5 are congruent by the transitive property of angle congruence. So there we have the alternate interior angle theorem. What does the alternate interior angle theorem say? How does it begin? If two lines are parallel and they're cut by a transversal, then the alternate interior angles are congruent. Okay? All right, now let's go to angle 1 and angle 7. I just wanted you guys to look carefully. Look at 1, 3, 5, and 7. What do you think? They're all congruent, aren't they? They're all congruent. Can we prove angle 1 and angle 7 are congruent? Well, we've already proven that 1 and 5 are congruent, haven't we? And what about 5 and 7? Why are they congruent? Vertical angle theorem. So if 1 and 5 are congruent and 5 and 7 are congruent, then what about 1 and 7? Transitive property. Alternate exterior angle theorem. Okay, so if two lines are cut by a transversal, if two parallel lines are cut by a transversal, then the alternate exterior angles are congruent. So we know about corresponding angles, they're congruent. We know about alternate interior angles, they're congruent. We know about alternate exterior angles, they're congruent. What was the last one we talked about yesterday? Consecutive interior angles. Okay, so consecutive interior angles, are 4 and 3 consecutive interior angles? No. How about 5 and 6? No. How about 4 and 5? Yes. So consecutive interior angles are always on the same side of the transversal, not on opposite sides of the transversal. So see how these two are on the same side of the transversal? So 4 and 5, and then 3 and 6, they're on the same side of the transversal. Do you think 4 and 5 are congruent? They're not. They're not congruent, are they? See, we've got one that's obtuse and one that's acute, don't we? Okay, so they're not congruent, not like the corresponding or alternate interior, alternate exterior. And I heard somebody say they're supplementary. Think that's possible? Okay, well, let's take a look. Let's see if we could somehow show that angle 4 and angle 5 are supplementary. Can we do that? Okay, so to begin with, let's just begin with, let's say angle 1 and angle 5. What do we know about those two? Okay, so let's just say angle 1 is congruent to angle 5. That would be the corresponding angles postulate. You okay with that? Might have to move this up a little bit here. Okay. What about angle 1 and 4? What do you guys know about 1 and 4? They're a linear pair, so they are supplementary. Okay. So angle 1 and angle 4 are a linear pair. That's just the definition of a linear pair. And doesn't that mean that they're supplementary? Angle 1 and angle 4 are supplementary. That's all linear pairs are supplementary. Why do we care about 1 and 4 being supplementary? We're trying to prove that 4 and 5 are supplementary. So if 1 and 4 are supplementary and 1 and 5 are congruent, so I think we could take this one and this one together into a new thought and say angle 4 is supplementary to angle 5, and this is the congruent supplements theorem. If two angles are supplementary to the same angle or two congruent angles, then they're congruent. This would be the converse of that, actually. Let's go this way for a second now. Let's just say I told you this angle is 30 degrees. What else does that mean? This angle? 30. This angle? 30. This one? 30. This one? 150. This one? 150. This one? This one? You're getting it. There's only two different angles here on these intersections, aren't there? Okay? Anytime we have two parallel lines and they're cut by a transversal, look at the angles. That one, that one, that one, that one. What do you know about all four of those? Yeah, they're all congruent. And then these two and these two here, are they congruent? Yeah, they're congruent. Okay? So let's take a look at example 2 on page 133 for a minute. You looking at that one? Okay. If you look at the two angles in blue with the 115 and the x plus 5, they don't fit one of our categories. They're not corresponding. They're not alternate interior. They're not alternate exterior. They're not consecutive interior. But remembering back to all of these angles have some relationship, don't they? What do you think about the 115 and the x plus 5?
They're supplementary.
Yeah, they're either going to be supplementary or they're going to be congruent. If you choose any two angles on the intersections, on either intersection, okay, any two angles, they're either congruent or they're supplementary. In this case, what are they? They're supplementary. And that's an equation. 115 plus x plus 5 degrees has to equal 180 degrees. We can find x. We can find the measure of each of those angles, can't we? Plus, I could even say this. X plus 5, just looking at it, doesn't it equal 65 degrees? I mean, if you subtract 115 from both sides, of course it is, but just looking at the picture, I might even go for that. Look at example 3. Once again, the two in blue, the 136 and the 7x plus 9, those don't fit one of our categories, do they? Okay? However, you got a big angle and you got a little angle. You got one that's obtuse and one that's acute. What do you know about those two angles? Yeah, they're supplementary. So again, we know they're going to add up to 180, and we can find the value of x, and we can find the missing angle there. Although, I know the missing angle is 180 subtract 136, isn't it? Yeah, it's actually just finding x there. Okay, turn the page over. So here's a formal proof on example 4. We're just going to follow this along for a minute. I got to go to the glasses on this one. This is proving the alternate interior angles theorem. I talked you through it a little bit, but here's a formal proof. I don't think this is the one we proved, is it? We have two lines that are parallel and a transversal, and you're given that P and Q are parallel, and you're to prove that angle 1 and angle 2 are congruent. So you notice they start out with their given information. Statement 2 is angle 1 and angle 3 are congruent, corresponding angles theorem. Now, I don't care if you call the corresponding angles theorem, if you call it a theorem or a postulate. I'm telling you it's a postulate, okay? But it doesn't really matter. Then vertical angles, and then the transitive property. If they're both congruent to the same angle, they're congruent to one another. Transitive property. 4 steps. There's your proof. Can you follow it through? Do you think that you could take that in today's assignment and maybe do the one for the alternate exterior angles? Now, do you think it's going to work pretty much the same way? It is. Okay, it's going to be pretty close to the same thing. I think you can figure it out. Now, let's look at the rainbow problem. When sunlight enters a drop of rain, different colors of light leave the drop at different angles. This process is what makes a rainbow. For violet light, the measure of angle 2 is 40 degrees. That's odd that we actually know the measure of the angle. What is the measure of angle 1? What?
40 degrees.
You guys solved the rainbow problem. Good job. Yeah, they're alternate interior angles, aren't they? Okay, there you go. I think you're ready. So, chapter 3.2. This is the assignment. I want you to keep in mind that every time that you think about one of these theorems, you have to begin with if two lines are parallel and they're cut by a transversal. If two lines are not parallel and they're cut by a transversal, do we know anything about the corresponding angles? We don't, do we? You've got to keep that in mind. If two lines are parallel and they're cut by a transversal, not just any two lines cut by a transversal. All right, let's get her done.